My name is Austin Fletcher. I am the group reporter for Group 2 for the internal combustion engine. This was experiment 4. The experiment was on a 13 horsepower, one cylinder, 420cc Predator engine. We performed 2 tests on it. The first one was a constant load with variable speed. First, we started the engine and brought it up to about 200 degrees Fahrenheit just to get it started and warmed up. Then we idled the engine and increased it to full throttle for 5 seconds under variable loads. We did four different loads of 0, 10, 20, and 30%, and we recorded the data for each of those. Here's the data from the runs that we got. At 0% is this graph right here, torque and horsepower. Started off at a very wide range right there. They became a lot closer together toward the end. That's about 3,000 horsepower. Here's the 10% load. You can still see a similar trend right here. And then 20 and 30%. The most interesting thing to take from this is that 30% horsepower actually overtakes the torque. Again, it's at that 3,000 RPM. We were expecting this to happen. From the equation, horsepower equals torque times RPM divided by 52. So we expected it to be at a different RPM, but for our purposes, this is a fairly acceptable answer. Now, we noticed with increasing load increases the torque and the horsepower. So while you might not be able to see the axes because of this presentation, but they do increase from the 20% to 30%. The biggest thing is also the, like I mentioned earlier, the gap between horsepower and torque closes as you increase in RPMs. So that's why this overtakes over here. The second test, it was a constant speed variable load test. We set it to 2,500 RPM, and then we started the load at 0% and brought it all the way up to 40%, and we repeated the run 3 more times after that. I'm going to focus in on our run 3, which seemed to give the best data. Our first run that we did seemed to start recording early, and so we would have had to trim it, and I just thought run 3 was the best run to use for these calculations. So this is it right here. You can see the corresponding peaks for when we increased the load percentage. At the very beginning, before the 10%, when it had 0% load, we had a lot of fluctuation in the data, which is expected since an engine is supposed to run with load on it. Once you increase the load, you can see it starts to flatline a little bit more. There is some jumble in the data, but you can clearly see every time you increase the percentage of load, you get a big peak in there. So the run time we did all the way up to 40 seconds right here. The torque and horsepower, you can see significant jumps, especially at 40%. You can see a very large jump right there. Now we did some calculations. I had to assume a few things. The air to fuel ratio that you see, A over F right here, I averaged out all of the data and it came to 13.98, and I decided to use that as opposed to it being a variable throughout. It did fluctuate no more than 1. So while I'm using 13.48, I did find the standard deviation for that was also, I believe it was 0.67. So when I was doing these calculations, I kept that in mind, and I would check it versus the standard deviation to make sure that these numbers were fairly accurate, and it turned out for the most part that they were. So this is the air mass flow rate in. Obviously, that's the air that's going into the engine that's being used by the engine to fuel the combustion reaction. So at 0%, it was 0.028. You can read it right there. Interesting enough, they didn't actually give us the units for it in the data, so we had to assume a few things. I tried to backtrace the units from the given formulas on the sheet, which I talked to a friend who was also in the internal combustion engine class, and he looked at some of the formulas, thought they were a little weird, but we went with what was given to us in lab anyways. So volumetric efficiency. Small engine, low loads on it, so we got really good efficiencies for this. I left the numbers not in percentages, so you can move the decimal place over, but we got 99.52, 99.5, things like that. So it was really good. The volumetric efficiency is the efficiency that the engine can move the air-fuel mixture into and out of the cylinders. So we got really good efficiency on that. Conversion efficiency, not so much. I ran through the numbers the first time on this and I didn't get the greatest, so I went back, found a mistake. Anyways, I got about 2% all the way up to 12.3% for the 40%. Makes sense because as we increase the load, we're getting better efficiency. There will be a sweet spot, but we didn't get to that. PB, again, had to make an assumption here. I assumed that was the power produced by the engine. So I converted the torque that we were given from the data, made that, put that all in there, and that's how I got these efficiencies. It's a ratio of fuel energy to actual energy produced. I think everybody should understand that. Mechanical efficiency, measured power that we got out of the system versus what it was rated at, 13 horsepower. So mechanical efficiency, again, 2% all the way up to 20%. Not bad. Not great by any means. Brake mean effective pressure. So we had this equation. Since this equation includes a lot of other earlier equations and calculations, this could, and the next equation has the most room for error in calculations by human, both calculation-wise and performed in the experiment. But I got a brake mean effective pressure that it does seem a little high, especially at 40%, at 482, but I feel like these are fairly comfortable numbers. The power, everybody knows what power is, that's what we got out of it. These are my calculated power values that I got from our data that I was using all the calculations earlier, and this is the power from the actual experiment that I converted over using this equation, and this was the one that given to us in the lab. You can see they're fairly similar. They're right outside the standard deviation that I calculated earlier. I didn't include that calculation on here, but they're fairly similar, and then you can see a graph of the calculated power versus actual data power. And they're fairly similar, but there are some fluctuations, and that comes from the errors. Like I said, operation error, calculation error, and then units and unspecified variables. So if we do this lab again, please specify the variables. It was PB was never specified. Anyway, that's it. Thank you.